Hello everyone, and welcome to the extended episode. I will start with a question by one of the viewers. Delker asked at the end of the premiere if all of this could be applied to C++, and the answer is absolutely yes, but you will probably need to be much more explicit in what you write. What Rayan does here in our code is it makes the whole abstraction of dispatching code to threads much more easier. First of all, on C++ side, you need to have your own thread pool implementation. Essentially, this functional way will not work because C++ is not meant for that. You need to manually push stuff to jobs. So right here, if you go to old matches parallel chunks, you would in C++ world, you would do something equivalent to this. So for chunk in old matches.chunks chunk size, and you would do thread pool .q job chunk, and you would call the function which is process chunk, and process chunk is a function that is essentially this whole body. That's the part where it processes chunk. Another thing you need to do is you need to manually make sure that you still have only one thread using one memory instance. So you would need to, instead of using this here, you would need to write a function which does clone mem. And what it will do, first of all, you need some sort of locking mechanism. So it will be mutex.lock. And then you do return equals mem.clone, which is one of the functions here. Right here, there is a clone function. Then you do mutex.unlock, and then you return red. That's what you need to do. You need to write this code manually, and you would initialize it inside process chunk void process chunk. You would initialize it by doing a, I believe, static mem equals clone mem. Static does initialize a variable in a thread local state. The issue with this, however, is that you need to somehow free it, and that's up to you to figure out how to free the memory without causing a leak. And that's the thing. In C++, it's absolutely doable, but it needs much more work ahead of time, much more, manual work, where in Rust you just do parallel extended. It just works. Not to mention collecting into a vector, you will need some sort of locking mechanism in place or a concurrent vector data structure, and that's also up to you to implement, but it's absolutely doable. It just takes a little bit more of work. Now, let's get on with this video. One bug I made right here is it shouldn't add a chunk size, it should add a chunk.length, because the final chunk couldn't be smaller than chunk size. So, yep. And now, once this is done, let's get on with the magical editing tricks to my past self. Let's tackle the initial search here. And the principle is the same. Essentially, what we do here is we convert it into a iterator chain, and we extend, we move this matches push from here into here as matches.extend. So let's do it one step at a time. This time you can see there are three for loops, which is exciting. Let's just make it like so. Self.matches.extend, and it will be this whole thing, and it will be Windows enumerate dot filter map. As usual, we have O and buff. That's the thing, and we just do sum address plus offset plus O, else it's nothing. Here we go. This is it. So this is the first loop done into extend. We need to do the same thing again here. So it will be self.matches.extend. and it will be here, and it will be essentially the same thing, flat map. It uses offset here, and instead of this, we move it here. We will fix the progress bar later on. We essentially return this iterator back down. So there are lots of errors. One thing is that this virtual read, it returns a result, and well, we can't use the result. There are two options. One is to just unwrap it or .ok it. Second one is to not do flat map, but instead do a filter map where we create a return thing and we just return some return. And this will be .ok here. That's the essence. Missing the final step, since we filter out bad reads here, we need to finally flatten the data. So it's the same as flat map, but we just kind of try filtering it out. Oh, okay, so now there is, as you can see, once again, the same issue of like borrowing the same thing twice. So we need to just collect it into a vector and convert it back into iterator. Boom, done. Done and dusted. And the final step is, well, what can I say? It's just moving this back out to be an extension here. And it will be self.memmap.iterator. I think it's a flat map once again. And we just take an address and size. And we have these. And that will be it. There's once again the issue of what exactly? Address is borrowed here. Essentially, we do the same thing we learned before, and that is a .collect into a vector and convert it back into iterator. You lose a little bit of performance by collecting and retransmitting it, but with small chunk sizes, it should be okay. It should generally be okay. Let's just see what the performance is like. 407 megabytes per second. It's faster. It could be slightly faster because we're not using the progress bar. So here's that, but we'll make the progress bar better. Now, the final step obviously is to just extend parallel iterator into parallel iterator and collect, and this one, the final one, is into parallel iterator. Or we also convert this into parallel iterator. What's the issue? Of course, it's the memory and buffers. We need to do the same thing here, so it will be ctx, ctx equals thread local context, new, where we move the buffer, the memory, and it will be mem.clone. Let ctx buff equals thread local context, new, and it will be a vector of 0 plus 1000 plus data.length minus 1. And it will be memory equals unsave ctx.get, let mid buff equals unsave ctx buff.get. And that's it. And now we run it. It's a bit sad that there is no progress bar, but we'll fix it. It doesn't show the progress. And did you notice how fast it was? I'll just run it again. It's 1.12 gigabytes per second. I'd say that's pretty cool. I'd say that is pretty cool. And yeah, we're doing progress. We're doing progress without progress bars, but we do progress. Oh, one time it was 1.47, so it's not very consistent, I could say. But from 240 megabytes to 1.12, 1.12 to 0.24, it's another 4.6x. Notice how it's 4.6x. Why is it a 4x speed up, not 32x speed up? Well, but yeah, essentially, you still have things on the main thread happening that you just can't parallelize. It's a limit, and you won't get perfect scaling all the time. You will get some scaling, but it won't be perfect. You have bottlenecks of collecting data, and you also have bottlenecks from just iterating it. There is a limit. There is a limit like going through the mem map. There is a limit of, going through chunks. There is a limit of, like visual reads. They saturate the same bus. If you have some log happening within the system call of reading, you're not gonna get perfect scaling. Because systems are not perfect. Threading is hard. As simple as this looks, actually, I think it's pretty tough to understand it, but like, once you get this, it looks simple, but then you go deeper and deeper and deeper, and things get pretty complicated. And like here, the same principle applies in, for instance, disassembler module. The same principle applies. Well, it's slightly different here because you have some... Well, this is a perfect example. This is where you have dependencies. For instance, here you have address as a dependency, which gets modified. And in a while loop, we're not doing a for loop because address depends on instruction lengths here. And that gets modified. So this here will be a perfect example of a slightly more difficult thing to multi-thread, but we're gonna do it right here and now. So right here you have what is 1, 2, 3, 4 loop. Four loops. One of them is a while loop, but it's 4 loops. And we need to just do the same process in reverse, but this part will be slightly trickier. I will show you. So the first loop is very, very simple. As you can see, we don't filter or do anything with it. We just do self.map.extend, and we pass through this like so, and this is gone. Now, it complains because it doesn't know what into we convert to. So we will just use address from to specify it that it's an address we want. And that's it. That's the first layer. Very simple, very trivial. Now this one is slightly trickier because we have a while loop which depends on this, which is not incrementing constantly. It goes by chunk size, but then it gets overridden right here with a different value. What are we gonna do? Well, one thing to note is that this will not make it differ by much at all. No. It will end up being, like 1 or 2 bytes over the chunk size. Like, what is it? Max instruction length is like 15 or something. Just 15 bytes here or there. I think that's good enough. I think that's, sustainable and usable. And we can just do a address to end step by chunk size. And then we do our typical, what is it? Flat map. I'd say flat map, but we have a virtual memory read right here. So we will use a filter map where we get the data, which we actually don't need. And we get this, we make this an OK. And then, well, we will just return this here. And we do that. And we will extend our thing here. Here we go. Yeah, oh, we need to do sum, and return like so. But yeah, now we have one more error, which is that we're missing a flatten. Right? And another error, which is that the data leaks out and gets used multiple times, which we solve by using .collect sec and converting it back into iterator. And that's it. We did the first two steps. Now let's do it again, which I think should be rather simple. We're going to do we have this p file thing, filter, and it will be a .flatmap, which takes in a section like so. We get rid of extend, we move the extend over to here. And we have errors, not an iterator, because we need to return it. Again, the same issue. Boom. Works. Wonderful. Yeah, we have that. And we finally have one final step here, and that is going through these modules. So it will be modules into iterator, .flatmap as usual, flatmap. It gets a module and it self.map.extend into it. We don't extend here, we instead return an iterator like so. Now, what is the issue here? I should return that or that, because once again this is the same type of issue. So it's filter.ok, oh, it's filter map, and we will actually move this back, and we will do let return equals this, and it will be some return. That's it, except for an issue. Oh, because we need to flatten it, finally. And one more error, which is this one. Two more errors. Oh well, two more errors. What's your problem? Follow borrows M. Well, as you can see, these are issues which we can solve by usual collection recollection. This solves it, and if we do echo G, we have 41 megabytes per second. If we undo this, let's see how it's same 40, 50. So it's the same speed, really. It's the same speed. I'd say it's 41, so it doesn't matter. Now, what we can do, obviously, is the multi-threading part. So we use the things from the prelude, from the rayon things, and what we're gonna do, a ctx equals, instead we do process.clone. Finally, ctx buff equals thread local context new, and it's ctx bytes instead. And also, let's not forget, and it's not mutable, these don't need to be mutable, ctx image, because right here we have one more thing for image, equals thread local context new move. No, we don't move it. Vector 0 size kilobytes 128, and we don't have these. we do borrow this here. Let mut image equals ctx image.get, which is unsafe. Let mut process equals unsafe ctx.get. This doesn't work because it probably needs to be as slice. Slightly different semantics. And finally we need to bind clone to this so that we can clone it. And then, okay, so now we need bytes. So here, it will be ctx bytes. Oops, it needs to be bytes. Okay, so this works. Now we just need to make it parallel. So it will be the same drill, parallel extend, modules, let's say, into parallel iterator. Where do we perform reads? We do that here. Lots of errors. We use something called parallel bridge, which essentially converts a regular iterator into a parallel iterator. This will be into par iter. This won't work. We need to use parallel bridge into parallel iterator. Yeah, this also needs to be into par iter. And we have an error, which is, I think it has to do with process. Yep, it has to do with process, because as you can see, we read memory here inside the process, and we also read memory here. So we need to access it from two places. So instead of using it once here, we need to also add it here as well. And that's where I think it should be alright. What's your problem? Oh, here's another issue. Because we modify address here, it cannot be parallelized. We cannot. So this needs to be a regular iterator, and we will move the access here. So instead of doing collecting into parallel iterator, we do this here with regular iterators. And that's it. And the final issue is the progress bar. We cannot have it. Now, if you run it, you will notice something very strange. Let me just enter password. Panics! Ooh, what is it? Already borrowed the value on thread. That's not good. You see, what happens here? We borrow the process, and we borrow it again, while this variable is still exists. It still is borrowed. So what you need to do is manually drop it. So we will just do a std mem drop, and it will be process. And that is going to fix it. Hopefully. Look at that. 270 megabytes per second, 250. Easy. Easy. This is so good. This is so fun. We did it. We did thread disassembler as well. What else? What else do we have? I think it's the offset scanner, that whole thing. Let's do that after the break. As for the progress bar, I'm not gonna do it line by line, but the very essence is that we're going to change it to be thread safe. That involves moving the actual progress bar into its own separate thread. What it does here, it essentially polls this this value, which is a count. It polls it and just sets the value of the count. That's all it does. And it does it every 30 milliseconds, so that it's not too fast, it's not too slow. And I just changed it, the methods, the functions, to essentially use this atomic variable. It's atomic so that the changes are atomically happen. And changes the atomic variable. For instance, we can do like add, we can do increment, we can do set, and we can do finish. When we finish, we essentially store a not zero, which is the highest value on the U64. We store that value and we just wait for the thread to join, which can take 30 milliseconds, which I'd say it's good enough. 30 milliseconds is rather short. So once you have that, you are able to add to progress bar with no problems whatsoever. It is that. We can remove this one. So this assembler works. We don't need mutability for the progress bar anymore. And right here we add that. We don't need it to be mutable. And right here we add that. And finally, oops. Finally, we don't need this progress bar to be mutable either. But that's it. Now, once we run it, I will probably need to recreate structs. Essentially, now, well, we run it. This was rather quickly, so let's do the other one. As you can see, beautiful. It shows perfectly. Like, it just looks. It's very fun to look at. It's very good user experience. You know the progress. You know what is happening to roughly 2 gigabytes per second. It's just incredible. It's just absolutely incredible. So yeah, that's about it, I'd say. Well, we have a couple more things to do. We have pointer map. How do we do pointer map in a threaded way? The exact same way we did before. This is our filtering method, which is very interesting, right? So what you do, Windows enumerate, and it will be a filter map. And it takes in an O and a buff. And this is what we will extend into. It will be a sum address out address, else it's a none. Okay, there is a bit of an issue. We need to return it, and that's it. This is as easy as it gets, and we need to do the same thing here, except we will do like the same thing as usual. It's a flat map, except this is a filter map where we get an offset. And we get the address plus offset, we get the data part, we .ok it, and we just move this out to here, extend, we do filter map, let's move this progress bar add over here, it's a Windows, it's the filter map, goes still here, we will do collect, as usual, we need to collect, and convert it back into iterator. And once that's done, we collect that out. This is a bit tough, so I'll just do sum red. Because, well, this is a bit much to wrap around. Let red equals. That's it. Now, dot extend. Yep. We need to do the final thing of .flatten. So we move it out, we flatten, and it works. We do the exact same thing here with the mem map. So it will be address size. It will be .flat map address size. And it will be a like so. One error is .iter. And that's about it. We just need to probably do recollect and convert it back into the iterator. That's it. We did it. Now we just need to obviously slap our multi-threading primitives, which will be, well, let's just run the pointer map first before converting. It should be quite a lot. time spent. As you can see, it's doing it roughly 64, 65 megabytes per second, which is good, but not too good, I'd say. While it's doing it, add the multithreading. So it will be par extend, its parallel iterator, dot into par iter. We do that, we read this part here. We could do parallel windows, but I don't think it's worth it at this point because it's just a single page. You will have overhead happening just by doing that. It will be here, though, that we convert it into parallel iterator, and this into parallel iterator. And what we need, the last thing, I think, yeah, we need to move this to make it plus clone. And once it's clonable, we will do a usual this plus size address minus 1. It's the same thing, size address minus 1. And then we just do ctx equals ctx.get unsave. Oops, it's a mem let mute buff equals unsave ctx buff.get. And that's it. So as you can see, it was 64 megabytes per second. Pretty round, I'd say. But let's see what happens now. What happens now? Whew. Did I just see 1.11 gigabytes per second? I think so. So, gigabyte 1.11 divided by megabytes, 64, that's 17x speed up. Boom! Which is much closer to the absolute limits we have since we've got 32 threads. But note that on computers, it's not real 32 cores. It's always 2 cores sharing the same resources. So that it is more efficient. As you can see, you get 17.76. You can actually run it with Rayon num threads equals 16, and we get 820 megabytes. So we don't get perfect scaling. So it's megabytes 818 divided by megabytes 64. We get a 12x speed up instead of a theoretical maximum of 16x. But by pushing even more threads, you can kind of catch up. And just to show you that it doesn't matter if you have like 64 threads, you don't get any more speed up anymore because, well, you don't have much more power. You don't have any much more oomph to give to the machine, to the code, and you can't make it any faster. So, like I'd say 24 would max out. No, it doesn't. Is it? Well, 30 threads. 30 threads max out when you've got 32 threads. So overall, this is it. This is wonderful, but now we have the final boss, which is... what is it? It's the offset scanner. How do we make this multi-threadable? How do we make this multi-threadable? I'm sorry to break it to you, but you can't quite easily. I know this is not satisfying. You can't. What's the difference? Why can't you? Well, the thing is that this function, walk down range, which is called by find matches, it is recursive. Right here, like all our loops, we're just splitting a for loop into smaller chunks and passing it over to the threads, and that's how you get insanely good parallelism. This here, though, find matches. It's recursive. It goes walk down range, and it searches things, and it's cool and all. We could try it, and I've done it in my tests, and the thing is, what you need to do very, very often here is do that recollection thing. And recollecting is fine when you do it at 3 steps, like right here. Collecting and recollecting happens once, twice, that's it, twice here. In Disassembler it happens 3 times. And it happens 3 times, that's the point, it happens 3 times. In recursive nature, you get, for instance, you recurse downwards into walk downrange. You have max level 5. At the level 5, you may get like 5 million calls. And there too, you would collect and create a new vector. And that creates a new vector every time, and you get millions and millions of vectors, and that's not sustainable, sadly. Which is very upsetting. But not much you can do about it. But it is a challenge. If you were to make this iterative, it could work. So if you want to go through the challenge, go ahead and make this iterative and make this fast with Rayon. And if you do, post it in the comments. I will check it out. You can put it on fork my repo, change it there. You can just post the code in the paste bin or GitHub gist or haste bin and send it over, or just post it in the comments if it's very short. But if you do that, well, I will feature it in the next video and just explain it how it's an interesting challenge to solve recursive algorithms and making them parallelizable. If you do that, you'll get heap points and unquestionable respect from everyone. So yeah, do that. I challenge you. But what we can do in the meantime, we can just... It finds it instantly. Let's do that. The depth 7. Here we go. This takes a while, right? Because, well, it's taking a while because it has also many addresses to check. As you can see, it has 92 addresses to check. So what we could do, we could kind of make up for it by making this, the initial loop, parallelizable. So it will be, well, it will be, we need to create a temporary vector. Let matches equals vec. That's the main change, and we will do matches.into iterator. That's what we will do, and we will just do a im, right? So it will be matches.extend.flatMap im, and that is it, I'd say. This is the change we're going to do, and we're going to make this parallelizable. So it will be parextend parallel iterator, yeah, into par iter. So that's the variations, and we don't need this to be mutable anymore because it's thread safe. Now, if you run this, here we go, that's my bad. So this, well, it took 1.1 seconds. If we do rayon num threads 1, as you can see, it's taking a while. This is so slow. How could we live with this slowness? Oh god, oh no, what did I get myself into? I mean, what did I get myself out of? That's a good question. How could I live with how? Ooh, this is slow. Ooh, this is slow. What can I say? I'm not looking forward for the next step. Well, it will be kind of fast. Oof, I should have just made it. Here we go. As you can see, it took 3 seconds. And if we go full bruh mode, it's very fast, it's rapid fast, and it's, well, these matches also take really fast. So essentially, if you've got many matches to find the offsets for, this is perfect. This becomes perfect when you've got many matches to find matches, offset links for. And yeah, that's it, I'd say. Is there anything else? There's probably this thing, that we make it immutable. But yeah, of course, right here you can see that the progress bar, it's not perfect by any means, because, well, it kind of jitters, but I'd say this is what we can live with. This is the guarantee of speed when it jitters. you know progress is happening when that happens, so yeah, I'd say that's a good sign. Like, that's a very, very good sign. If we just make it very deep, I think we will just have jumping around. Yes, perfect. You don't know what's going on. Neither do I. Neither does he. You just know that progress is being done. That's about it. Yeah. Oh, look it. I think it will be done soonish. Maybe. I don't know. Who knows? Alright, so we finished. I hope you understood it a little bit. I hope you learned a little bit more about this whole thing with multithreading. I hope it helped you a lot. Don't forget to overflow the like button. It helps the channel absolutely tremendously. And hit subscribe for more videos like this. And I'll see you very soon, actually. Don't forget, my name was Heap. Yours wasn't defined. See ya.